and welcome to the second video of the ISTQB Certified Tester Foundation Level Preparation course. My name is Dmitry, and I'm a Creative Manager at Exactpro. Today, we will cover Chapter 2, Testing throughout the Software Development Lifecycle. Software Development Lifecycles, or SDLCs, are quite fascinating. Some of them are lightweight and fast, and so we follow them when time to market is of the essence. Others can be controlled, documented, and preferred in spheres where quality and reliability are the key factors. As we mentioned in the previous video, testing is context-dependent. So the choice of SDLC is often tied to what we are testing. It is important to be familiar with SDLC models to be able to choose the appropriate one. A fit-for-purpose model can save time and money, helping deliver a quality product. No matter which lifecycle model is selected, there are several characteristics of good testing. For every development activity, there should be a corresponding testing activity. Test analysis and design for a given level should begin during the corresponding development activity. Testers should be involved in reviewing documents as soon as drafts are available. And each test level has test objectives specific to that level. And let's not forget that no matter which development lifecycle is chosen, we perform validation and verification. Verification is all about the requirements. It makes sure that every one of them is fulfilled. In a nutshell, verification focuses on the question, is everything built according to the specification? Validation, on the other hand, centers on the user's needs that were the reason for writing the requirements. It answers the question, does it provide the solution to the problem? The ISTQB Foundation level syllabus divides all life cycles into sequential and incremental. A sequential model describes the software development process as a software development lifecycle model in which complete system is delivered in a linear way of several discrete and successive phases with no overlap between them. This means that a new step should begin when the previous one is completed. Incremental development means that the software features get updated by adding functions to the previous release until all functionality is implemented. The waterfall model is one of the oldest ones. It has a natural timeline where tasks are executed in a sequential fashion. So all development activities, for example, requirement analysis, design, coding, testing, are completed one after another. In this model, test activities only occur after all development activities have been completed. It is easy to manage, and the process should be well documented. And that is the blessing and the curse of this model. If we don't have clear-cut requirements from the start, it becomes increasingly difficult to support. It is hard to get feedback passed up the waterfall, making it virtually impossible to correct the mistakes made early in the life cycle. Under these conditions, the price of an error can skyrocket. This obvious disadvantage led to the development of a more adaptive V model. Unlike the waterfall model, the V model integrates the test process throughout the development process, implementing the principles of early testing. Moreover, the V model includes test levels associated with their corresponding development phases, which further supports early testing. In this model, the execution of tests associated with each test level proceeds sequentially, but in some cases overlapping occurs. This model shows that testing is not only about the test execution. Component testing focuses on units that are separately testable. Integration testing focuses on interactions between the components or systems. System testing focuses on the behavior and capabilities of the whole system or product, often considering end-to-end tasks the system can perform and the non-functional behavior it exhibits. Acceptance testing, like system testing, typically focuses on the behavior and capabilities of the whole system or product. All test levels will be covered later in this video. But the problems start when the requirements have to change, because the V model still supports linear software development and has a limited built-in ability to respond to adjustments. The other issue is that the testing is constrained by rigid timeframes. It also promotes a strict link between the corresponding levels of coding and testing, rather than encouraging testers to choose the most effective approach. Both of the sequential models put out software that contains the complete sets of features, but typically require months before the end product could be presented to its stakeholders. The iterative or incremental models are more flexible. Their development involves establishing requirements, designing, building, and testing a system in stages, which means that the software features grow incrementally. The size of these feature increments varies, with some methods having larger pieces and some smaller pieces. The feature increments can be as small as a single change to a user interface screen or a new query option. The aim of such development model is to get feedback as soon as possible, which decreases the cost of defects. But the iterative development model has its flaws. It is not suitable for some sorts of software to be released with a small number of functions. Examples of iterative models include rational unified process, where each iteration tends to be relatively long, for example 2 or 3 months, and the feature increments are correspondingly large, such as 2 or 3 groups of related features. Then there is Scrum. Each iteration tends to be relatively short, for example hours, days, or a few weeks, and the feature increments are correspondingly small, such as few enhancements or 1 or 2 new features. Then there is Kanban. It's implemented with or without fixed-length iterations, which can deliver either a single enhancement or a feature upon completion, or you can group features together to release at once. And finally, Spiral. It involves creating experimental increments, some of which may be heavily reworked or even abandoned in subsequent development work. The constant need to adapt to changes in requirements brought forth the publication of the Manifesto for Agile Software Development. It called for a new approach where changes could be implemented in small increments to facilitate immediate feedback from end users and technology specialists. In 2001, the creators of the manifesto proclaimed that they were uncovering better ways of developing software by doing it and helping others do it. Through this work, they came to value individuals and interactions over processes and tools, working software over comprehensive documentation, customer collaboration over contract negotiation, and responding to change over following a plan. The next thing we need to cover in this video is test levels. The ISTQB syllabus identifies 4 of them: component testing, integration testing, system testing, and acceptance testing. Let's look at what happens at each of them separately. Component testing or unit testing focuses on individual hardware or software components. So basically, it searches for defects in modules that are separately testable. Objectives of component testing include reducing risks, verifying whether the functional and non-functional behaviors of the component are as designed and specified, building confidence in the component's quality, finding defects in the component, preventing defects from escaping to higher test levels. In some cases, especially in incremental and iterative development models where code changes are ongoing, automated component regression tests play a key role in building confidence that changes have not broken existing components. Component testing may be done in isolation from the rest of the system, but most often stubs and drivers are used to replace the missing software and simulate the interface between the software components. A stub is called from the software unit under test. A driver calls on the unit under test. Component testing is usually performed by the developers themselves. Sometimes, writing automated test scripts may precede writing the application code. Examples of typical defects and failures for component testing include incorrect functionality, for example, not as described in design specifications, data flow problems, and incorrect code and logic. Bugs are typically fixed as soon as they're found, often with no formal defect management. If developers report defects, this provides important information for root cause analysis and process improvement. The next level is integration testing. It is a test level that focuses on interactions between components or systems. For example, if we're integrating module A with module B, the tests should focus on interoperability between them, not the functionality of the individual modules, since that should have been done during the component testing. Integration testing may be performed on 2 stages: component integration testing and system integration testing. The first one is performed by developers after the unit testing is done. The second one is performed by testers after or during the system testing. There are two integrational approaches, Big Bang and incremental. Integration strategies may be based on the system architecture or its functional tasks. One can perform integrations from top to bottom and use documentation. If component does not exist yet, it can be replaced with a stub. Bottom-up approach is similar, but missing components are replaced with drivers. Functional integration means integration of functionally connected units. In order to simplify defect isolation and bug detection early in the SDLC, integration should be incremental, adding a small number of components at a time, rather than a big bang, which is assembling all components at once. The greater the integration scope, the more difficult it becomes to isolate defects to a specific unit. Continuous integration often includes automated regression testing, ideally at multiple test levels. Objectives of integration testing include reducing risks, verifying whether the functional and non-functional behaviors of the interface are as designed and specified, building confidence in the quality of the interfaces, finding defects, which may be in the interfaces themselves or within the components or systems, preventing defects from escaping to higher test levels. Examples of typical defects and failures of system integration testing include inconsistent message structures between systems, incorrect data, missing data, or incorrect data encoding, interface mismatch, failures in communication between systems, unhandled or improperly handled communication failures between systems, incorrect assumptions about the meaning, units, or boundaries of the data being passed between systems, and failure to comply with mandatory security regulations. After that comes the system testing, which is a test level that focuses on verifying that a system as a whole meets specified requirements. This level of testing focuses on the behavior and the capabilities of a whole system, its functional and non-functional requirements. System testing is typically carried out by independent QA teams based on specifications. Specification inconsistencies can lead to a lack of understanding of expected system behavior. Such situations can cause false positives and false negatives, which waste time and reduce effectiveness. The early involvement of testers help to mitigate such issues. Objectives of system testing include reducing risks, verifying the functional and non-functional behaviors of the system, validating that the system is complete and will work as expected, building confidence in the quality of the system as a whole, finding defects, preventing defects from escaping to higher test levels, or production. Sometimes verifying data quality may also be an objective. Examples of typical defects and failures for system testing include incorrect calculations, incorrect or unexpected system functional or non-functional behavior, incorrect control and/or data flows within the system, failures to comply and completely carry out end-to-end functional tasks, failures of the system to work properly in the system environments, failures of the system to work as described in system and end-user manuals. The last but not the least is acceptance testing. It is a test level that focuses on determining whether to accept the system. Acceptance testing, like system testing, typically focuses on the behavior and capabilities of a whole system or product. Objectives of acceptance testing include establishing confidence in the quality of the system as a whole, validating that the system is complete and will work as expected, verifying that functional and non-functional behaviors of the system are as specified. In other words, the questions acceptance testing answers are: what, if any, are the outstanding business risks? Can the system be released? And has development met their obligations? There are different forms of this kind of testing. Common types include the following: user acceptance testing, operational acceptance testing, contractual and regulatory acceptance testing, and alpha and beta testing. User acceptance testing of the system is typically focused on validating the fitness for use of the system by intended users in the real or simulated operational environment. The main objective is building confidence that the users can use the system to meet their needs, fulfill requirements, and perform business processes with minimum difficulty, cost, and risk. The operational acceptance testing of the system by operations or systems administration staff is usually performed in a simulated production environment. Contractual acceptance testing is performed against the contract's acceptance criteria for producing custom development software. Acceptance criteria should be defined when the parties agree to the contract. Contractual acceptance testing is often performed by users or by independent testers. Regulatory acceptance testing is performed against any regulations that must be adhered to, such as government, legal, or safety regulations. Regulatory acceptance testing is often performed by users or by independent testers, sometimes with the results being witnessed or audited by regulatory agencies. For instance, the financial system is obligated to store transaction information for 10 years. System will not be released until it's proven that it is capable of storing such amount of data. Alpha and beta testing are typically used by developers of commercial off-the-shelf software who want to get feedback from potential or existing customers before the software product is put on the market. Alpha testing is a type of acceptance testing performed in the developer's test environment by roles outside the development organization, and usually done on-site. And beta testing is a type of acceptance testing performed at an external site to the developer's test environment by roles outside the developer organization and is often conducted at testers' locations. Project teams can employ various forms of acceptance testing during each iteration, focused on verifying a new feature against its acceptance criteria and on validating that a new feature satisfies the user's needs. Examples of typical defects for any form of acceptance testing include: system workflows do not meet business or user requirements. Business rules are not implemented correctly. System does not satisfy contractual or regulatory requirements. Non-functional failures, such as security vulnerabilities, inadequate performance, efficiency under high loads, or improper operations on a supported platform. Next, let's talk about a different approach to test classifications by types. A test type is a group of test activities based on specific test objectives aimed at specific characteristics of a component or system. Such objectives may include evaluating functional and non-functional quality characteristics, as well as the structure and effects of change. Functional testing of a system involves tests that evaluate functions that the system should perform. It is a kind of testing performed to evaluate if a component or system satisfies functional requirements. Functional requirements may be described in work products such as business requirements, specifications, epics, user stories, use cases, or functional specifications, or they may be undocumented. The functions are what the system should do. The thoroughness of functional testing can be measured through functional coverage. Functional coverage is the extent to which some functionality has been exercised by tests. Functional test design and execution may involve special skills or knowledge, such as knowledge of particular business problem the software solves. According to the ISO standard, ISO IEC 25010, functional testing can show a system's functional completeness, functional correctness, and functional appropriateness. Functional completeness shows how the system covers users' requirements and needs. Functional correctness means that the system works correctly and how precise the results of its operations are. Functional appropriateness characterizes the closeness of the system functions to users' needs and aims. There are two perspectives from which testing functionality can be done. Requirements-based testing means that testing is performed according to the requirements in the specifications. Business-based testing means that testing is performed according to the tester's knowledge of business scenarios and needs. And then there is one additional perspective. Experience-based testing means that testing would be outside the written requirements. It's testing something that business can consider as not a very likely scenario, but testers' experience tells the opposite. Non-functional testing of a system evaluates characteristics of systems and software such as usability, performance efficiency, or security. Non-functional testing is performed to evaluate that a component or system complies with non-functional requirements and answers the question of how well the system behaves. Non-functional testing can and often should be performed at all test levels and done as early as possible. The late discovery of non-functional defects can be extremely dangerous to the success of a project. Non-functional test design and execution may involve special skills or knowledge, such as knowledge of the inherent weaknesses of a design or technology or the particular user base. According to ISO standard, ISO IEC 25010, non-functional testing has the following characteristics. Performance, which has three sub-characteristics: behavior over time, resource utilization, and capacity. The first means checking if response time, performance, etc. meet the requirements. The second means checking if resource utilization meets the requirements. The third means checking system limits, for instance, max transaction count per day, max user count in system, etc. There are three characteristics which are not mentioned in the ISO standard, but they're important. Load. It's a kind of non-functional testing. Like performance testing, it also checks the behavior over time, resource utilization, and capacity, and is focused on the system's capacity of dealing with expected load. Stress testing also uses all three sub-characteristics of performance testing, but focuses on the system's capacity of dealing with peak load, which is higher than expected. And then there's scalability. It needs to determine if system is capable of growth. Let's go back to the ISO standard. Compatibility is about a system's compatibility with other software. Usability is about the ease and comfort of use of the system. Reliability refers, for instance, to the system's behavior during hardware or software failure. Security refers to the system's security, and maintainability refers to the system's maintainability. Users are not the only ones who are working with the system. There is also technical support, administrators, etc., who maintain the system's work. Small changes should be easily done for them. Portability refers to the system portability. It means how easy it is to move the system from one platform to another. White box or glass box testing is based on the analysis of the internal structure of the component or system. It derives tests based on the system's internal structure or implementation. Internal structure may include code, architecture, workflows, and data flows within the system. The thoroughness of white box testing can be measured through structural coverage. Structural coverage is the extent to which some type of structural element can be exercised by tests. At the component testing level, code coverage is based on the percentage of component code that has been tested, and may be measured in terms of different aspects of code, such as percentage of executable statements tested in the component, or the percentage of decision outcomes tested. These types of coverage are collectively called code coverage. At the component integration testing level, white box testing may be based on the architecture of the system, such as interfaces between components, and structural coverage may be measured in terms of the percentage of interfaces exercised by tests. White box test design and execution may involve special skills or knowledge, such as the way the code is built, how data is stored, and how to use the coverage tools, and how to correctly interpret their results. When changes are made to a system, either to correct a defect or because of a new or changing functionality, testing should be done to confirm that the changes have corrected the defect or implemented the functionality correctly, and have not caused any unforeseen adverse consequences. A type of testing initiated by a modification to a component or system is called change-related testing. There are two types of this kind of testing. Number one is confirmation testing, or retesting. It's a type of change-related testing performed after fixing a defect to confirm that a failure caused by the defect does not occur. And number two is regression testing. It's a type of change-related testing to detect whether defects have been introduced or uncovered in unchanged areas of the software, with its purpose being to verify that modifications in the software have not caused unintended side effects and that the system still meets its requirements. Confirmation testing and regression testing are performed at all test levels, especially in new features, changes to existing features, and code refactoring result in frequent changes to the code, which also requires change-related testing iterative and incremental development life cycles. This is especially relevant for Internet of Things systems, where individual objects are frequently updated or replaced. Regression test suites are run many times and generally evolve slowly, so regression testing is a strong candidate for automation. The last thing we're going to talk about in this segment is maintenance testing. Maintenance testing, by the way, not to be confused with maintainability mentioned earlier, is testing the changes to the operational system or the impact of the changed environment to an operational system. These tests are executed on the software that is already deployed. It is necessary because software systems that have been released into live production typically remain in service for a very long period of time. They still get updated and upgraded to keep up with new requirements. Otherwise, the system will quickly become obsolete. Because of this, failure to do maintenance testing may result in accumulation of errors, which in turn will render the system unusable after a number of upgrades. Maintenance is also needed to preserve or improve non-functional quality characteristics of the component or system over its lifetime, especially performance efficiency, compatibility, reliability, security, and portability. When any changes are made as part of maintenance, maintenance testing should be performed, both to evaluate the success with which the changes were made and to check for possible side effects in parts of the system that remain unchanged. Maintenance testing is testing the changes to operational systems or the impact of a changed environment to an operational system. By environment, we mean a setup of software and hardware. So a test environment is a set of software and hardware for the testing teams to execute test cases. These tests are triggered by modifications, migration, or retirement of the system. From the testing point of view, there are two types of changes. One is planned modifications, that is pretty much self-explanatory. They comprise over 90% of all maintenance work on systems, and unplanned corrective modifications, which deal with defects requiring an immediate solution. For example, a production run which dumps late at night, or a network that goes down with a few hundred users online. There are several reasons why software maintenance and thus maintenance testing takes place, both for planned and unplanned changes. We can classify the triggers for maintenance as follows. Modifications, such as planned enhancements, corrective and emergency changes, changes of the operational environment, upgrades of commercial off-the-shelf software, and patches for defects and vulnerabilities. Migration, such as from one platform to another, which can require operational tests of the new environment as well as of the changed software. Or tests of data conversion when data from another application will be migrated to the system being maintained. Retirement, such as when an application reaches the end of its life. When an application or system is retired, this can require testing of data migration or archiving, if long data retention periods are required. Testing restore retrieve procedures after archiving for long retention periods may also be needed. And let's not forget that regression testing may be needed to ensure that any functionality that remains in service still works. Impact analysis is the identification of all work products affected by a change, including an estimate of the resources needed to accomplish the change. It evaluates the changes that were made for a maintenance release to identify the intended consequences, as well as expected and possible side effects of a change, and to find the areas in the system that will be affected by the change. Impact analysis can also help to identify the impact of a change on existing tests. The side effects and affected areas need to be tested for regressions. This concludes the second chapter of the ISTQB Foundation Level Preparation course. Good luck with your studies, and I'll see you soon at Chapter 3.